Okay, so I think let's get started. Now we are going to look at some code in XP6 for the remaining part of the lecture based on whatever concepts that we just learned. Okay, so we're not going to a lot of details because this is the last 30 minutes of the class and I can already see that most of you may be tired right now. Okay, so we'll have it at a pretty good level at least. Okay. So what we're going to do is, let's just see where does the kernel start. Okay. The kernel starts in a file called kernel main.c. Okay. Again, I'm skipping a lot more details about how does the system boot and stuff. Okay, you need not worry about those things right now. But let's assume somehow the system started booting and the operating system started executing on that particular system. And here we are in the main function of the operating system, and it's right here. Okay, and then it calls a bunch of setup. It does a bunch of setup, and finally it calls a function called jump stack. Okay, I'm just going to that function. Again, the shortcuts that I'm using here are just control and like close square brackets. These are like C tags shortcuts. And I would definitely recommend you guys to use any like code indexing software to make sure that you navigate XP6 in a better way. But definitely the tools that we are going to use for navigating XP6 really reduces the amount of time that you're going to spend understanding the XP6 code. If you are going to do a grep for each and every function that you're going to search, then it takes a lot of time. Okay. So now we are in a function called jump stack. And it has some details here, and one thing to note here, okay, is there is some assembly code. Line number 36 just says there is some assembly code. ASM stands for assembly. It's a directive for assembly code, and we can write some assembly code directly here. And inside this, there is one call to a function called main.c. Okay, there's a call to a function called main.c, and here main.c is right down. Okay, you can just see main.c here. So it is moving something to the stack pointer, but again, don't worry about it. Yeah, we have stack pointer is starting at the 0 address. But again, those are like details that we really don't worry about. Okay, but let's see. But for you to like understand for each and every project, you'll be actually understanding much more details. But one bad way or like one inefficient way to look at this is like, for example, let's say for P1B. Even for that project, you may go into details of each and every line of code. But again, you're going to spend a lot more time concentrating on stuff that we really don't need. So it is like an art to figure out like what is the piece of code that we really want to focus on for doing a particular thing. Because it is like a huge code base. I mean, comparatively huge and compared to at least. Okay, whenever I'm talking with you guys, I'm thinking of like the UW students. Okay, you may be like working with much more bigger code bases than this, but maybe this is like, yeah, okay. But this is again maybe a small code base for you, but it may be like much more involved or something like that. Okay. So here we have this main.c, another function. It does a bunch of initializations. Okay. It does some things with the interrupt controller and a lot more things. We need not worry about these things, but one thing that we would be interested in is this TV init. Okay, TV init again stands for trapped vectors init. If we go inside that particular function to see what is going on, it is actually, this piece of code is actually initializing the trapped vectors. We saw like there will be some trapped vectors that interrupt descriptor table, or the trapped vector table that we saw in this particular diagram. Is that particular thing. Okay, so here in this trap vector or the interrupt vector table, here we have 256 different, in XP6 we have 256 different trap vectors, or there are like 256 different indexes in that particular table. Okay, and it calls some function called setgate. If you go inside these things, these will be like bit level manipulations. Okay, it specifically sets those memory locations with certain bits in a particular way, so that the hardware, when it wants to like when we are trapping into the operating system, the hardware just says run this particular again, you need not, okay, for example, you can just take a look at this code, but you really need not worry about understanding this code, okay? If you want, you can. No one is going to stop you, but from the purposes of this course, this level of detail is not needed, okay? But I'll let you understand like which level of detail is needed. So this is what is happening here. So the trap vector in it just does that, okay? It does that. It just sets up the trap vector table in the memory. After doing that, it does.
Is that always in the memory, or is that ever stored on the CPU, like in hardware?
No, it is in the memory.
So like
yeah, it is. Yeah, the interrupt descriptor table is like a bunch of things.
Like on the RAM.
Yeah, on the RAM, exactly, on the physical memory. Okay. But it will be stored at some special location,
yeah,
so that the operating system informs that location to the hardware. And then it goes and does much more initializations, which we really don't need to worry about. And line 58 is slightly interesting to us because this is where the timer interrupt is being initialized. Okay, this is the line where the timer interrupt is being initialized. I'm not going into that right now. Okay, but again, after doing all these things, we call something called CINIT. You see something called CINIT, right? It's just right below here. And inside that CINIT, you have a thing called, again, whenever I'm just talking about something, it means that other things are not really needed for our discussion right now, okay? So here we are concentrating on IDT init. IDT again stands for interrupt descriptor table. We are trying to initialize interrupt descriptor table. So inside this, it just calls a thing called LIDT, okay? This is like a special instruction. LIDT is a special instruction. It is actually this particular assembly instruction called LIDT. This is a method, okay? This is just a function name here in the kernel, but inside this there is some assembly, at line 78 there is some assembly instruction called LIDT. This is a special assembly instruction that is used by an operating system on x86 to inform the address of the interrupt descriptor table to the hardware, okay? This is the instruction that informs the address of the starting address of the interrupt descriptor table to the hardware. LIDT again just stands for load interrupt descriptor table. Again, don't worry about the details about what is happening here exactly, okay? This is the idea, this is the thing that's happening here. Then, once this is done, then we enable the interrupts on this particular computer. Then we call thing called user init. User init is the function which is used to create the first user process, okay? And in the next lecture, we will go into details about how to create the second user process, the third user process, and stuff like that. But the first user process is created in a special way by the operating system, and it is called the init process. And I think this may be helpful right now. So usually the operating system creates this first user level process called init process, okay, which has a PID of 1. And then init creates the next process called the shell process, which is nothing but the shell that we see when we start x86 operating system. You see like a command prompt there. That is nothing but a user process called the shell. And it has a PID of 2. And then whenever you type in a particular program, let's say hello or some C program that you type in, that will be the third process that is created. So in this hierarchy, here the parent of the process hello is shell, and the parent of the process shell is init. Okay? So in your P1B, basically, when you run a program like this, and when if you call the system call get PPID, it should return what value? If you are running get PPID in hello, PPID again stands for parent PID. It should just return the value of 2 because the parent process's PID is 2. This is all we are asking to do in P1B. Okay.
Yeah. So last week you were doing the thing where you called like several copies of the same program into multiple processes in the background. Yeah. With all of those sharing the same parent.
Exactly.
Okay.
So when we are running like multiple processes, Okay, let's say P1, P2, P3 are run together from the same line in the shell. All P1, P2 and P3, there is no like relation between them, among them. They are like siblings basically. There may be relation, they are siblings, but they all P1, P2 and P3's parent was the shell program. Was the shell, okay? Good questions. Now let's switch back again here. Yeah, and then after the first user process is scheduled, after the first user process is created, now the operating system, the kernel starts or calls a function or a module called scheduler. And this is the scheduler code, which we will not go into the details right now, but this is how a scheduler is in x86, okay? So let's assume, now we are making some assumptions here, okay? The scheduler starts running, the first user process is created. What do you think will be the state of that first user process? What will be the state of the first user process when it was created by the operating system? Is it ready or running or blocked or some other things? Okay, at least out of these three things, what do you think it should be? Ready, exactly. We just created it and it is ready to run. Okay? And so when the scheduler starts running, the scheduler, if you go through this code, but we're not going to go through this right now, the scheduler just chooses one of the ready processes and just starts scheduling. Okay? But currently, there is only one process in the whole system, only one user level process, so the scheduler has no other option but to schedule that first user level process. Okay? And when the first user level process is scheduled, then that creates a second user level process, which is the shell program. And at that time, the scheduler has two options. You can either schedule init or the shell. And that's when the policy decisions come into place. Which one to schedule, kind of. So now, at a very high level, we are going to assume we are having two processes here, okay? A and B. Okay, we are having two processes here. And let's assume process A is currently running. Okay, let's assume process A is currently running. And when process A is currently running, we suddenly have a timer interrupt. Okay, this is the scenario that I'm creating so that we can go through the code tracing this particular scenario. So there are two processes, A and B, and currently process A is running, and while process A is running, there is a timer interrupt that just happened. Okay? You have a question? So for that, I would start tracing the thing from a file called vectors.s. Yes, again the extension S stands for assembly, C stands for C, and O stands for object file. Okay, this vectors.s is the actual interrupt descriptor table we saw, right? We saw something like we set up the trap vectors, like there will be 256 trap vectors that are set up by the operating system for handling each and every type of interrupt, and the system call was nothing but one type of interrupt, right? So in this particular thing, you see here there are like from 0 till 255. There are 256 different vectors that are being set up here. Okay, and we were interested in the timer interrupt, and I just told you timer interrupt corresponded to the vector number 32, right? You may go and figure out like how that is valid. I can show you in some time, but when you do the timer interrupt vector, so when you come to this particular trap handler for the timer interrupt, it pushes some two values on the stack. Okay, it pushes a value of 0, which is the error code. Again, details are not needed, and it pushes the value of that particular like interrupt number basically. The 32 is the number for the timer interrupt, pushes that on the stack, and then immediately it calls a routine called all traps. Now we are going inside all traps. Again, we are still in assembly code. You can find that out using the name that is here at the bottom of this file, or just looking at that, you can easily see if it is so messy, if it is like so different, it's going to be assembly, and here you have like trap.asm.s is the file that we are in, and this is the file. Then we just jump to this particular function called all traps, an assembly function. And here it pushes like these 4 registers, and here these 4 registers are called the segment registers. Okay, these 4 registers are called the segment registers in the CPU, and this push AL just means push all the general purpose registers. So the single instruction in turn will actually push the registers EAX, EBX, ECX and all these registers to the stack. Okay, so this is where, okay, we are actually storing some context. Okay, we are storing some context of process A on the kernel stack, and the stack that we are storing in, whenever we are pushing something, we are storing on a stack, right? The stack that we are currently storing these details are the kernel stack of the particular process. You may skip these things. Again, there are some more things that are being done here. Don't worry about these details. This piece of code is mainly here to maintain backward compatibility with the previous machines and stuff like this. So again, we are not worried about these things. Okay. So but this is really important. After doing this, we push something like we push the some ESP register, the value of the current stack pointer. We push that particular thing on the stack. Let's see why that happens later, but then after that we call a function called trap. Okay, so when we call this trap, I'm just going to the trap right now, control and close bracket. So now we have come into the world of C programming. Okay, this trap is a C code. Okay, this trap function is a C function. Now we are here. Okay, this is the function that is called inside the operating system whenever we trap into the operating system due to a system call or interrupt or any type of interrupt. Okay, but here we are assuming we have trapped into the operating system due to the timer interrupt. So we come here, so we immediately check. Okay, we immediately check, did we trap? So the trap number is saved inside this trap frame that we just passed in here. Okay, don't worry about that right now, but we are just checking, is this trap number that we just trapped into the operating system, is it due to a system call? And what will this number be? T underscore syscall. What do you think is the value of T underscore syscall? Exactly, it's going to be 64. You can see here in a file called traps.h that the value of T underscore syscall is nothing but 64. Okay, but now we just came with the value of 32, right? And so this is not going to be equal, so we are just skipping this. But for your P1B, this is some piece of code that you may be interested in, because you are, interested in the sense, okay, one thing I forgot to mention is like P1B, so project 1B for adding a system call, you can even get it done in less than 30 minutes, really, just by copying code from an existing system call. But if you really want to understand and do it like in a very good way, I would say like at least it would take like somewhere between 4 hours or something like that, around 4 hours or something, if you really want to understand what is going on in each and everything. So you may follow the discussion sections. How many of you were there for the discussion section yesterday? Okay, so where you did, what did it happen in the Enders game room? Okay, was it enough for all the people who were there?
Yeah.
Okay, great. And for your information, the discussion section is also posted online. The video of the discussion section is also posted online in our course web page. If you missed the discussion or if you did not watch the video that I sent you during the weekend, either one should be fine. Either watching that video or attending this discussion section should be fine. But if you missed those things, again, the videos are here. Okay, discussion P1A, P1B is here. You can go and click those links to watch those videos if you want. To help you with this particular thing. Okay. Let's continue. So now we did not come here due to a system call, but we came due to a different thing. So we are switching on the trap frame number, okay, the trap number. So the trap number is 32, so that is nothing but we would enter this case, IRQ0 plus IRQ timer, because actually IRQ timer would be, IRQ0 would be 32, IRQ timer would be 0. So that is the reason I just told you the timer interrupt has a value of 32, because all the interrupts start at a base value of 32. Okay, these interrupts start at a base value of 32, this is just at the offset 0 from 32. So now this case would be hit, and we are doing some acquiring and releasing of a lock here to update some variable called ticks. Ticks is just the number of ticks that the we are just maintaining the ticks that are passing. Okay, so we will see like why are we doing this later, but this is not needed right now. And after this, we break from this case. So we go to the end of the switch, and go to the end of the switch. The switch ends here. Okay, and after that is the most interesting thing. So now you see here. Okay, we are just going to check in line 102. We are just going to check if that process is not null, which means the process is still running or in some state. Okay, proc just refers to the PCB of the process. Proc here just refers to the PCB of the process. Proc is present, the proc state is running. Okay, it is running, and if the trap number is equal to IRQ0 plus IRQ timer, which is nothing but 32, just call the function called E. You remember we told this like long back at the beginning of the class. We call a method called yield, and you go to yield, and here yield just says give up the CPU for one scheduling round. So we acquired some lock, and then okay, the reason why we are acquiring and releasing locks here are like these data structures are shared across different schedulers in a multi-processor environment. x86 is a multi-processor operating system. So if we have like 2 CPUs, okay, there will be one scheduler for each CPU. And we don't want these 2 schedulers to mess up the data structures in any way. Okay, if there is no lock, they can easily be messed up. That is the reason we are acquiring lock before we do something. Okay, and then we set the state to be runnable or ready, because we are going to switch from this process. We are going to stop executing process A, and we are going to start executing process B. Is that right? That's what we are going to do, right? And so we just change the state of the current process. Always proc just refers to the currently executing process. In our scenario or in our example that we are considering, it is nothing but process A. Okay, so A.state becomes runnable. Then we call a method called sched. It is inside a file called proc.c. So we go inside sched, and it does a lot of checks. Don't worry about these things. But at the end, it calls a function called switch. Okay, sched at the end calls a function called switch. So and this switch, line 305, we are saying there are 2 arguments. Okay, this means that first argument means the currently executing process. Second argument means the process that we want to execute next. Okay, so the switch at line 305 just means we are going to switch from process A, because proc is just A according to us, right? We are going to switch from A to the scheduler, to the CPU scheduler. Okay, and how does that switch work? Let's go into switch and see. Switch is a assembly code, as you can guess. Okay, switch is assembly code here, and it does a lot of things. I think if I go into this detail right now, it may not be the correct time, because I think I should do this at 5:30, this particular method, but I will try explaining it at a high level, and maybe in the next class while starting, we'll just start from here. Okay, we'll just start from the switch, because the switch is so interesting. Okay, but at a high level, what is happening is, here we are just switching we are just saving the callie save registers of process A. So do you guys remember the convention, x86 convention of caller saved registers and callie saved registers? Whenever, so the idea is whenever a function is called, there is the responsibility of saving the registers is split between the caller and the callie. Caller saves certain registers like EAX, then the other registers that are not here. Basically, the caller saves the registers EAX, EDX, ECX, okay? And it's the responsibility of the callie to save these registers. So basically here we are just saving the callie save registers, and then in these 2 lines of assembly code, we are actually switching the stacks, okay? We are actually switching the stacks. By switching the stacks, here, conceptually what is happening is currently the stack pointer is pointing to the stack of process A, right? The kernel stack of process A. So maybe I think this diagram may help here. So the scenario we are considering again is just process A, okay? Process A is here, and we have process B, and in between we have the scheduler, okay? And each of these things has like two levels. This is the user level and this is the kernel level. Initially we were executing at the user level of process A. This is the user thread, okay? These two different things we name it as threads of execution. So this is the user thread of process A and this is the kernel thread of process A. So we were executing here. Suddenly what happened, this was the first thing that was doing. Suddenly a timer interrupt happened. Timer interrupt happened, this is step 2. Then so immediately we switched from the user level to the kernel level of process A, right? When we were the code that all the code that we are seeing till now was some code in this here, okay, here, because we were executing at the kernel, but with respect to or in the context of process A, okay. And so at that time, the stack pointer would have been pointing to the kernel stack of process A. Now we just saw that the switch method is going to switch from process A to the scheduler. So scheduler has its kernel thread running here. So now the stack pointer, okay, stack pointer initially was pointing to here. Now in that switch stacks, we are going to just switch the stack pointer or make the stack pointer point to the scheduler, to the scheduler's stack, scheduler's kernel stack. The scheduler is a part of the OS, yeah. It's not a separate thing. It's just a part of the OS. So basically we are just making the thing point to some kernel stack of the OS.
Does the OS have several kernel stacks? Like for different processes like scheduling and other things?
So when the kernel is running, only one, it can be only active at one point in time. I mean like one place in the code it would execute only one line of code at a time. So
but like for like something else that it could do besides scheduling, does it have a different stack for keeping track of that?
no. There's only like one kernel stack for this. So here we are just switching. The next thing is switching from the kernel stack of this or the kernel thread for process A to the scheduler's kernel thread. And now what is going to happen? We are performing a context switch right now from A to B. Will we jump to the user thread of the scheduler?
Save the callee registers?
Yeah. So just one question here is like, is there even something called the user thread of execution for the scheduler? No, there is nothing called the user thread of execution for the scheduler because scheduler is a component of the operating system. Operating system only exists in the kernel mode. Okay, so there is nothing called the user level thread of the scheduler. So all that is going to happen here is there is going to be another switching of stacks between the scheduler to the kernel thread of process B. So this is the next step that happens, and then now from here we will be switching back to the user thread of process. So this is what is happening, and this line 4 where we make this actual transition is these two lines, the stacks, the switch stacks, right? So I can't just explain these two lines independently because it depends so much on whatever is happening before from the piece of code that we were tracing till now, okay? So that was the reason I really don't want to like go into those details currently. and I even like don't think that we may have the time to like go into these details, and these are like really this level of detail is like very interesting for you, for everyone to understand if you really want to understand operating systems. But we are not going to like test, we are not going to do this piece of code in exam and ask like, okay, can you explain this or something like that. Okay, you need not really worry about assembly code in this course. Okay, but only if you understand assembly code, you will really understand operating systems in depth. Okay, that's the idea here. So that is the reason. Okay, let's assume this. Do this. Let's assume now the stacks are switched, which means that we have. So once the stacks are switched, once these two lines 20 and 21 run, what is the next thing that is going to run? So currently we came here. We called the switch routine from the context of process A. Okay, we call the switch routine from the context of process A. Let's assume now we have finished executing line 21. So now, after finishing executing line 21, what is the next thing that is going to run? Is it the scheduler, or is it the kernel thread of process B, or user thread of process B? Yeah.
We're going to load the registers into the stack for the scheduler kernel so that it can run.
Exactly. So that is happening here. So basically, we are going to execute the scheduler. We are going to be in the context of the scheduler.
So look on top L, because we've implemented the stack pointer, these are different registers.
So these pop things that are happening here, okay, when the scheduler first came to process A, we would have stored these things using the push. So now, since you're going to run the scheduler right now, you're going to pop the values from the scheduler's kernel stack. So these four values that are being popped are actually popped from the scheduler's kernel stack. So once these two lines are done, we have actually switched stacks. Okay? And so when we pop these things from the scheduler's kernel stack, and when you return from here, okay, when this return is executed, okay.
So it's obviously not the ones that we just pushed out.
Pardon?
I mean, it's not the ones we just pushed out. Right?
Yeah, it is not the ones that we just pushed on the stack, okay? That's a very good observation. So the things that we push here, we are pushing to the kernel stack of process A, okay? But since we just switched the stacks, we made the stack pointer point to the kernel stack right now, kernel stack of the scheduler right now, the lines 24 to 27 are actually popping things from the scheduler's stack. Okay, from the scheduler's stack, scheduler's kernel stack. And so when we return here, where will we return? When this return instruction is executed, where will we return?
Instruction for the scheduler.
Exactly, we are just going to return to wherever the instruction pointer of the scheduler points to, okay, of scheduler. So we are not going to return here, okay, that's a great thing about this. We just jump from here, okay. Switch is not like a normal function call, okay. Switch is not a normal function call. You switch, you started switch, but you don't just return and start executing line 306. Instead, I will just show you where we will return. There is a function called scheduler, okay, which is the actual scheduler code, which we already saw a little bit. So in this scheduler code, when the scheduler was executing, when the scheduler first initially started executing process A, it again called the same switch method here. You see this here, line 277. When the scheduler was executing, it just called the same switch method, but at that time it just told, I want to switch from the scheduler, which is me, okay, to process A, or the currently, yeah, in our case it was process A, okay. Or you may think of it like when you want to switch from A to B, you just came to the scheduler, okay, you will just return at line 278, then you will go through this loop, this for loop, pick the next process that is ready to run, which is nothing but process B, okay, let's assume it's process B, just pick that process, and then now you will switch from scheduler to process B. So that return that we just saw there would actually return to line 278, because sometime before we had switched from here. Now we return here. Yeah, isn't it cool? Awesome, right?
So, are the two parameters for switch actually just the stack locations? Is that how that works? Wait, what actual piece of information is the first parameter there?
So it is a pointer to a structure which has some details about the scheduler. You may just go and look at the CPU.scheduler, right? So if you want to just
And is
this one. So this is the structure. It is per CPU state. Okay, and this is the structure. Again, you may like look at this to understand better, but the idea is you may think that okay, it is switching from the scheduler somehow to the process A. But for you to understand much more, you have to just look at these things again at a high level.
I can follow up. We're almost out of time. I can ask you after.
Okay, great. So this is how it's happening, and I'm not very sure if I will be able to like go into the details of this because we would like I'm not sure if we would have the time in the next class or so. But so what I would suggest is instead of this fall 17, just change this to if you are interested, because I hope like everyone is interested. If you're interested, just you may go here to summer 17 and you see this or I can send you an email with the exact timing, but for the details that we're talking about, I can give you a glimpse of how like interesting or how involved it may be. Or just leave it. I just have the thing from the last semester. We will be like we actually built the entire thing there. What happens internally on the stack. So this is the process A's kernel stack. Just think if I had done this like in the last 30 minutes, I think people would have left or something. Okay? So this was, we actually built this like step by step to understand how this was built, and corresponding to the code, just go and watch the lecture video that I send you if you are interested. And again, these are the registers there, and this is the scheduler stack. And this, after doing that, only part of the context switch actually happens. Then for the remaining part to happen, you had to again switch from the scheduler stack to the process B's kernel stack. And then only a complete context switch happens. Makes sense? So I don't think we will have the time to explain these things. If I have, I can definitely, I will try to explain. Else, I will send you a link to the video. You may take a look at it. Again, it is like not like necessary, and these things, we are not going to test these things on the exams, okay? These specific details here. But again, since you are so interested in operating systems, you should definitely take a look at it, okay? Okay, so that's it. I think crossed the time. Yeah, I have that video.